class 11th physics, chapter mechanical properties of fluids. Generally we call it liquids, but more specific term is fluids. And today's topic is viscosity. So earlier we have discussed about different type of flows, and I have a separate video on that. I will put its link in the description. You can check. All right, so now what is viscosity? So first I will explain you what is this term is all about. So if we take some water into some tumbler or bucket and we whirl it, then we can often see that most the part which is in high speed, which gains that speed, is on the topmost region, and in the bottommost region speed is very low. It appears like and okay, after some time it comes to into rest. How it happened? So actually what happens actually, it can be defined in terms of different layers. Suppose there are different layers in the liquid which do not intermix, and that is why this kind of flow we call laminar flow. So between these different laminas there is a kind of force which opposes their relative motion. So that is why this layer is moving with high speed, this layer is not with that speed, this layer even less, and so this is the order in which relative velocity between different layers is decreasing, and this property is called viscosity. So the property by the virtue of which relative motion between different layers of fluid is opposed is called viscosity. So if that relative motion is opposed, that must be opposed by some force. That force is called viscous force. So next topic is viscous force, F subscript V. So the force between different layers of liquids which opposes relative motion between them, actually different, we should not write it two times, between them, is called viscous force. So mathematically there is a relation. This viscous force is directly proportional to area of cross section, area of surface of liquid. And one more thing, a new parameter is there, delta V by delta X. Generally it is written with negative sign. I'm avoiding writing that. Here delta V by delta X is called velocity gradient. It means change in velocity with respect to distance. And as I told you that in different layers, velocity in the topmost layer is highest, then it goes on decreasing. So delta V by delta X is velocity gradient. It is explaining that with the depth on going downward, how velocity is decreasing. So combining both of them, we can say viscous force is proportional to A. This is as a whole single term. These are not two different things. This is together a single term. So this eta, a proportionality constant, A delta V by delta X, where this eta is equal to F upon A delta V by delta X. This eta is called coefficient of viscosity. And what is its unit? So first we'll discuss about its SI unit, and that is equal to unit of force, that is Newton, upon unit of area, that is meter square, unit of velocity, meter per second, and unit of again distance, meter. And when we simplify it, it will come out to be Newton second per meter square. So Newton per meter square into second, which is also called Pascal second. And this is also called Poiseuille. Quite difficult name. If it is quite difficult, then there is a short form for this also, Poiseuille. And in CGS, this entire thing will change like this: Dine second per centimeter square. So there's no replacement for Pascal in CGS, so we'll move on. It is poise. This is called poise. So if we talk about how many poise are there in one Poiseuille, so one Poiseuille is equal to 1 Newton second upon meter square. So this is 1 into 10 to the power 5 Dine second upon, so it is 100 centimeter square. So it will give 4 powers of 10. So finally it will be equal to 10 Dine second per centimeter square, and which is equal to 1 poise. Sorry, 10 poise. So 1 Poiseuille is equal to 10 poise. So what about its dimension? It is also important. Dimension of force mlt minus 2, dimension of area L2, dimension of velocity Lt minus 1, and upon dimension of length. So ultimately it will be m. L will get cancelled, this will go up, so it is L minus 1. This T minus 1 will go up, so this is T minus 1. So its another unit can be kg per meter per second. This also you can remember. Alright, there is another law by which we can find viscous force acting on a body moving through a fluid, that is moving through a liquid or moving through a gas. That is why collectively I am calling fluid. So, well, actually, the expression given by Stokes is applicable, effectively applicable, I would say, effectively applicable for spherical bodies only. But yeah, of course, it gives a rough idea for any other object moving through that medium or moving through fluid. So let me first explain what is this law states. So viscous force experienced by a spherical body varies as follows. A spherical body moving through a fluid, moving through fluid varies as follows. So F is directly proportional to eta, is the first thing. So more is the viscosity, more is the viscous force. F is proportional to radius. Bigger the object, more is the viscous force. And F is directly proportional to V also. Higher the velocity of object, greater will be the viscous force. So if we combine all of them, we get this expression, eta RV. So there's a proportionality constant, 6 pi eta RV. There's a derivation of this expression with the help of dimensional analysis, but I'm not doing it here. It is already done in dimensional analysis chapter. So you can go and check that video also. I will put its link in the description. Well, so what does it mean? It means if there's a fluid and this body is moving through it with some velocity v, so of course it will experience some force which will oppose its relative motion, same as frictional force. But there is a difference. Frictional force is not area dependent, whereas frictional viscous force depends upon area, as we have seen in previous expression. Here it is depending upon size of that object, that is radius. But what if there is not the spherical body but some other shape, maybe square, a cuboid, or cylinder, or any other object? Still, this law is not accurately be applicable, but somewhat up to a certain extent this will be applicable. Means still force will depend upon coefficient of viscosity, force will be depending upon velocity of that object through that fluid, and if it is not a sphere, then maybe some factor of size that will matter. Like if this is moving and this is moving through a fluid, then obviously it will experience more viscous force. So for other objects we can not quantitatively, I mean not by exact computation, but we can assume, we can estimate the order of that force. Okay, so next there is another term, very important one, which is called terminal velocity. V subscript T. The maximum constant velocity of a freely falling body in a fluid under gravity is called terminal velocity. Well, there is an activity in which you can drop a coin, just holding it like this, and then drop it in a water tank. So first that coin appears to move very fast, and then it looks like it is its velocity is decreasing. So actually what happens here, terminal velocity, I'm directly doing the derivation so that you can easily understand the concept of terminal velocity. So let us suppose we consider a case in which this object, this round shaped object, is moving through the fluid with velocity v. So there are three forces acting on this body. First one, its weight, I write it Fg. Second, buoyant force acting upward, Fb. And third thing, viscous force again acting upward, Fv. So in a freely falling body, actually vertically falling body, why I'm not saying freely, because now it is under the influence of buoyant force and viscous force, so now it is no longer freely falling. Vertically falling body in a fluid, body will experience three forces. Number one, weight downward. Second, buoyant force acting upward. And third, viscous force acting upward. What is the formula for weight? Fg is equal to mg. And what is this mg is all about? That is density into volume. Density of body into volume of that body. Why is it so? Just go through the formula for density, then you will come to know. Volume 4 by 3 pi r cube into g. Now next, buoyant force. Buoyant force is the force of weight of water displaced. So remember, mass of water displaced, that will be different from mass of that body. That is why mw I have written here. Now see, water, well, it is a fluid, so I'm putting, okay, f, mf. So density of fluid into volume of fluid into g. Actually, in buoyancy, buoyancy is what? When an object is immersed into liquid, it displaces some water or some liquid, and that displaced liquid or displaced fluid exert actually liquid exert pressure, and exerted force on that object is equal to the weight of water displaced by the object. There are two things. First thing, volume of object is equal to volume of water displaced. This is the first thing. Second thing, buoyant force is equal to weight of water displaced. So these are two things here. Keep these things in your mind. So this is the weight of fluid displaced. I always habitually write water, but consider it as fluid. Fluid displaced. Weight of fluid displaced. So that is why volume part is same in both. Once again I repeat, if I have a ball, I immerse it into some fluid, then the displaced fluid will have volume same as the volume of that ball. So that is why V in both side, 4 by 3 pi r cube g. And what about viscous force? It is 6 pi eta r v. Now see, this is a constant force, this is a constant force, but this force keeps on increasing. Until when? Until, see, there are two forces in upward direction. However, this can be very, very greater than both of them. But there is a possibility that if viscous force increases, and let us suppose this Fg was earlier 10 Newton, this buoyant force was earlier 5 Newton, and this viscous force has started first 1 Newton, then 2 Newton, then 3 Newton, then when both of them will equal to 10 Newton, then net force on this body will be 0. What I am saying, these two forces are constant, they will not change, but this is continuously increasing as it is moving through the fluid. The speed will increase, but as its speed will increase, viscous force acting on it will also increase. So upward force is increasing. There will be a situation when net force acting on that object will be 0. At that time, its speed will become constant, and that is what written here: maximum constant velocity of freely falling body in a fluid. Well, freely word is subjected to some risk. Vertically falling, I will correct this, vertically falling body in a liquid. Okay. All right. So when V equal to Vt, that is when net force is equal to 0, and that is when this Fg is equal to Fb plus Fv, or what we can do, Fg minus Fb equal to Fv. Then if we put these values here. So I'm doing it directly because there are so many terms which I can take common. So it will be 4 by 3 pi r cube g will taken as common. Rho b minus rho f is equal to fv 6 pi eta r v subscript t. So this is the expression for terminal velocity. So we can give a final touch to it. So vt is equal to 2 3s are 2 2s are, so it will be 2 by 9. Pi will also get cancelled, r1 power will get cancelled, so it will be equal to r square, 1 power has gone, g rho b minus rho f upon eta. So this is the expression for terminal velocity. Next is critical velocity. The maximum velocity up to which flow of fluid is uh, is remains streamlined is called critical velocity, denoted by V subscript C. So, well, critical velocity is directly proportional to eta, means coefficient of viscosity, and inversely proportional to density of fluid and diameter of pipe through which it is flowing. Eta, coefficient of viscosity, rho, density of fluid, and d, diameter of pipe through which fluid flowing. So here we have very special constant r subscript n, eta upon rho d, where Rn, which is equal to Vc rho d upon eta, is called Reynolds number. And remember one thing, if Rn is less than 1000, there is not a clear boundary, but roughly if it is close to 1000 or less than that, then the flow is streamlined. And if Rn is greater than 2000, the flow is turbulent. And Rn 1000 to 2000, it is unsteady. Yeah, we can say turbulent, but unsteady is most appropriate, and unpredictable. And unpredictable. It can be streamlined, it can be turbulent in between. There's not a clear boundary, but we are certain about less than 1000 it must be streamlined, above 2000 it must be turbulent.